So a summary of the procedure we saw so far can be made as follows. Let's consider that we have a function W, which is a function of X, Y, and Z. In thermodynamics and physical chemistry, as you will see, it's quite common to have functions of 3 variables. Not so much of 2, not so much of 4. You might see 2 more often than 4, but 3 is the most common scenario, and there is a profound reason for that, which you visit in thermodynamics. So the typical procedure is to decide which variables are dependent and which variables are independent. It's quite possible that all 3 are independent, then life is simple. You don't have to worry about the things done in this module, but typically one of them depends on others. So you eliminate this dependence. If Z depends on X and Y, you take that functional relation into account and you remove it. Once you have eliminated it, then you differentiate as usual. This is what we saw in the example so far. So let's see what it means in practice. Let's consider to have a function W, where this function W is defined as x squared plus y squared plus z squared. So let's consider a point over here, x comma y comma z. So you can see W represents the square of the distance between any such point and the origin. You could draw a straight line and it is the square of the straight line. That gives you W. But now let's introduce a restriction, which is a constraint that any such xyz must lie on a paraboloid, which is a parabola rotated along the z-axis, given by z is equal to x squared plus y squared. So in red here, I have tried to draw that paraboloid. And so now this xyz point that I drew first is, for example, not allowed. You must have a point that lies on this surface somewhere, anywhere on this surface. So let's say we are restricted to this surface, and now we are interested in calculating partial W by partial X. So partial W by partial X at a point XYZ. So this over here that I'm highlighting in blue is the point XYZ. And we want to calculate the partial W by partial X here. What does it mean? Let's say this point is equal to 1, 0, 1 at some point. So this partial W by partial X can now be calculated in 2 ways. It can be calculated by keeping Z is equal to constant. If that is the case, you would move along this blue line that I'm highlighting again, right? Because this is the line which corresponds to same value of Z. If you do this, then you can see clearly that in this case, we have Z is equal to constant, and the line that we are moving on actually corresponds to a circle. And what is special about a circle? X squared plus y squared is equal to constant. So if Z is constant and x squared plus y squared is also equal to constant, then W is not changing. Therefore, for moving along this line, that is partial W by partial X at constant Z is 0. And you can go and put this, and I invite you to go and do that, plug in the math here and see that you get that relation. You could think of another partial W by partial X, which is by keeping Y constant. In this case, we move along this black line. And in order to understand this, you have to really imagine a plane given by y is equal to constant. So if we move along the black line, it's easiest to imagine if you consider y is equal to 0. In this case, you just get this. Let me use a different color over here. In this case, you get this plane, right? That is the plane y is equal to 0. So the black line, as you can see, is where the plane intersects the paraboloid. So as you're moving along this line, now you can see that x squared plus y squared is actually changing. So the value of z along this one, z squared plus x squared plus y squared is actually changing. Therefore, partial W by partial X, when keeping y constant, in this case, we just took the example y is equal to 0. It could have been some other constant value of y is changing. And therefore, this is not equal to 0. And you should go and calculate what is the exact value. That brings us to the end of this module. Thank you very much.